Last time I spoke about Poisson structures on manifolds, and I finished at the last thing I discussed last time was a theorem which says that a bivector field pi defines a Poisson structure if and only if the bivector field verifies the equation pi and pi commute with respect to the Schouten bracket. So that was the last thing I discussed. I think it's proposition, not some big theorem still. And this proposition says that a bivector field pi defines Poisson structure if and only if this holds. When I say the bivector field defines some structure, I mean that we put the Poisson bracket of f and g to be equal to the value of pi on differentials of f and g. So this proposition, I think I proved it, almost proved, because actually I just deduced it from the following formula, which is due to Lichnerovitsch. Suppose you have a differential form omega of degree p plus q minus 1 on a manifold M, and two vector fields, two polyvector fields, p and q, in the space of polyvector fields on M. And in particular, p is p vector field and q is q vector field. Right? Then following formula holds. The pairing of omega and the Schouten bracket of p and q is equal to the following linear combination of brackets. So first of all, we use the sign minus 1 to the power p minus 1, q minus 1, I think, di q of omega paired with p. Then we need to subtract dip of omega paired coupled with q and add minus 1 to the power p, I believe, the pairing of d omega with the wedge product of p and q. So I think I need to say a few words about how this theorem can be, this formula can be proved before I proceed. And so let me sketch some major steps in the proof of this theorem. So first of all, I think it is very useful to extend the notion of contraction from vector fields, of contraction of differential forms with vector fields to contraction of polyvector fields with differential forms. So for me, IP is more or less a contraction from differential forms on M to differential forms of degree less by p in the original degree. And roughly speaking, I think not so very roughly speaking, if p is equal to the batch product of q vector fields, of p vector fields x1, xp, then this ip is equal to just the composition. Only the sign should be taken care of, but I think if I just write it from left to right in this way, then it will be okay. Because contraction, if you remember, they anti-commute. Contractions of with respect to vector fields anti-commute, just like these factors in the wedge product of vector fields, right? AXP. In this case, what we have here can be written as the contraction of omega with the with the Schouten bracket of P and Q, right? And on the right, we'll have this following combination. I P D I Q omega minus IQ D I P omega and plus minus 1 to the power p I p wedge q of omega. And there are evident formulas like I p wedge q is equal to IP wedge IQ, sorry, followed by IQ, or the opposite direction, whatever. Also, have something which is similar to the Cartan's magic formula. So you remember the Cartan's magic formula says that the Lie derivative with respect to the vector field x is equal to the commutator of differential and contraction with x. Right? So same thing can be yeah, plus, sorry. Yeah, that's much better. Yeah. Sure, it's graded commutator. So since both are of degree 1 and minus 1, so non-zero degrees, of course we have plus, sure. That's much better. In the same way, we can define the Lie derivative with respect to p as the linear combination of differential and contraction with p, but the sign here will depend on the degree of p. I think it's p minus 1, right? Yeah, IP D. I'm not sure about this, so this sign is a little bit of conjecture. So we can now try to rewrite this. For instance, here what we have IP D IQ omega, right? And it is equal to IP D IQ omega plus minus 1 to the power q minus 1 IQ IP, sorry, D omega. Yeah. But of course, this element is artificial, so we need to subtract it again. So it is minus or plus minus 1 to the power q IP IQ omega d omega. So this is equal to IP LQ omega plus minus 1 to some power q IP IQ IQ omega, right? I just need to check if the sign is correct, but we need to. Okay, so when we add this sign here, what we get? It is equal to minus 1 p minus 1 q minus 1 I p LQ omega, right? And this sign plus q, so what is it? It is p times q minus 1, something like this, I believe, right? So if we add q to this, what do we get? It's p minus 1 times q, okay, just something like this, p minus pq minus p minus q plus 1, and we also subtract q, right? Something like this. Up to the sign is just p q minus 1 plus 1, which I don't quite, I'm not quite sure it is this, but it is something like what we need. So in any case, well, just the signs, I'm not sure about the signs. Let us just, I'll restore the signs for in some particular cases where the signs are easy to compute. But this is more or less just kind of guess. Please check it. Then when you do all the computations in terms of these contraction operations, you'll have on the right-hand side something like IP LQ omega plus IQ LP omega, right? And plus or minus. And L P HQ omega. I think that's something like this. That's what we get. So the right-hand side here can be contracted to something like this. And then, if everything is correct, then then this I think it is even without the last term. Yeah, I think it's something like it's something like this. IQ, IQ, yeah, IP, something like this. So if everything is correct, we get something like this, if everything is correct. And then we have the following equation, which is almost evident. Just like in the classical situation where we have just the vector fields, we take the commutator of Ix and Ly, right? Or vice versa. And what you get will be a contraction with respect to the commutator of x and y. And the same will appear here. The same thing will emerge here. This combination on the right, this right-hand side, will be equal precisely to the contraction with P and Q. So that's actually the proof, more or less. Right? So you just rewrite the right-hand side with proper signs, of course, in terms of contractions and the derivatives with respect to polyvector fields. And then you use this kind of formula, which you can actually prove using this formula and also the decomposition of I and Q in terms of vector fields. So that's very easy, in fact. Okay. Let us check this formula in some particular case where it is simple. For instance, I want to convince you that this method actually works. That's actually why I got late today. I was trying to guess proper signs. So, you know, choosing signs is hard. So let us take X and Y to be just vector fields. So they're just polyvector fields of degree 1 on M. So what do we have? We have the contraction. And now we have any one form, right, on M. And we need to check that the contraction of omega with two vector fields, with the commutator of the vector fields, can be expressed in terms of contractions, just like prescribed by Lichnerovitsch formula. So here we have minus 1 to the power 1 minus 1 times 1 minus 1, that's 0, so no sign here needed. We just have omega d I think y omega, right? And x here minus d I x omega y. And minus, because it's minus 1 to the power p, right? And p is equal to 1. Omega contracted with the wedge product of x and y, right? So what do we have? D omega, of course, d omega. Yeah, d omega, not omega, d omega. So the first element is very easy. When you contract one form with a vector field, you just obtain the value of this vector field, of this one form of vector field, and you differentiate and contract this result with x. That's just x of y, of omega of y. Just this, right? Now we have the same here. Now y of omega of x. And finally, we have minus d omega. This contraction is just the value of omega on x and y, d omega of x, y. But now, by Cartan's magic formula, it is equal precisely to x of omega of y minus y of omega of x and plus and minus omega of the commutator of x and y. Right? So when we substitute this, we get just omega of x comma y, and that's precisely what we need to obtain, right? Also, you can do this in case where, say, x is still a vector field. So there's just this, and y is equal to a function is just a 0 polyvector field. And again, you can do this by direct computation. So what you have on the left is, so f omega is again some smooth function g. Differential 0 form is just full function. And when we contract g with commutator of x and f, by definition, you remember it was equal to x of f, and this contraction is just the product of this function with g. nothing else. That's the definition of contraction. You can extend it here. So what do we have on the right, on the other hand? You take differential of the product of f and g, right, and substitute it into x. You get just x of fg. Again, the sign is non-existent because one of the fields is of degree 0, of degree 1. So 1 minus 1 is 0. Minus, now this sign is constant, and that's a relief. But however, whatever, when we contract a field with a function, we get just 0, so this is non-existent at all. So what we have is finally f of x of g. And as you see, it is precisely the left-hand side of this formula. So again, everything matches perfectly well, and I just need to check that the signs are chosen correctly. You see, all the rest is done by this manipulation with the derivatives and commutators, graded commutators, contractions, differentials, and so on. That's more or less the standard thing you do. Okay? I hope it is a good exercise, actually. just choosing correct signs is a bit of a problem, but you can think. I think you can find it in many textbooks. But people who write textbooks, they usually care about signs much more than I do. But if you look into some papers by, for instance, Maxim Kontsevich and other people like he, you'll find just plus and minus everywhere. Because taking care of the signs is quite a nightmare. Okay, so let us go on. So that was that which was left from the last time. Now we go on. I think I need to explain a few moments about the Poisson structure. So first of all, definition. First, for any function f on a Poisson manifold, we can define its Hamilton vector field of f is x sub f given by definition. So there are two ways you can do this. X sub f applied to g is equal to just, well, it depends on the sign, but I prefer the plus sign, of course, f g. Sometimes people put minus here. You should be careful. Sometimes not. And it is, of course, the same as to say that xf is the raising of the indices of the differential of f with respect to the bivector, right? Easy proposition is that xf, when we apply the derivative with respect to xf to any to the Poisson bivector, you get 0. That's 1 and 2. The commutator of xf and xg is equal to x of Poisson bracket of f and g. So let us prove the first thing, for instance, the first part, for instance. What do we do? It's actually quite simple. You just rewrite this formula as follows. So we know that it is this, but it is the same as to say that the Poisson bracket, sorry, the Schouten bracket of pi and f is equal to x sub f. I don't know if it is really necessary to prove, but let us do this. I think just to show you how this is done. So how do you do this? I just use this formula, right? So what do you have? By the properties of Poisson bracket, sorry, of Schouten bracket, this is equal to xf of g, right? By the properties of the Schouten bracket. On the other hand, if you substitute, so let's put x tilde to be equal to the Schouten bracket of pi and f. Right? We can do this, right? Then let us substitute this here. What do we have? Pi f g. Just a moment. Oh, I think it's easier. Sorry, I just have a little, I already have Lichnerovitch formula, right? Yeah, I have a Lichnerovitch formula, so let me just use this. Sorry, I was trying to prove Lichnerovitch formula again, but that seems stupid. So what do we have? I want to find dg. So what is xf of g? It is what is this? It's the pairing of this and this, right? Let me put tilde here. So let me denote this by x tilde sub f. So this is equal to what? By Lichnerovitch formula, which is true here, right? So this is dg, and I have x and f. Sorry, pi and f by definition, right? What is it equal to? It is equal to minus 1 to the power p minus 1. So 1 and 1, right? So it's just minus 1 minus pi contracted with d of if of dg, which is of course 0, right? When you, because, sorry. No, sorry, it's not 0. It's not 0. Minus 0, the next one will be 0. Minus d I pi of dg. And this is 0 because this is one form. Right, and I take two forms here. So this is okay. This is okay because it is one form in the vector field, but this is two form, so it's not okay. This is 0. F. And finally, we have plus minus 1 to the power p, so that's just plus d dg pi times f, which is 0 because d square appears here. So I eventually get minus sign. Okay. Okay, but that's correct. So let's put it this. Let's we'll get it, right? So this minus is important after all. So what we have here is what? It is minus d of f dg, right? Minus f dg, contact it with pi, which is precisely pi of df dg. That's just the definition. So that's just the process, the bracket, Poisson bracket of f and g. So this formula is proved up to the sign, which I believe should be like this. Minus is equal to this. Okay. So now, in order to prove part 1, what do we have? We substitute, well, I would actually ignore the sign here, just put pi f pi into the formula, right? That's what we have. And it is equal by the, how do you call this? The gradient Jacobi identity, right? It is equal to plus or minus, let me put it like this, pi, comma f minus, and this sign is important. And unlike this sign, which is totally, well, unimportant, which is totally redundant because the commutator of pi and pi vanishes identically. This sign is important, and please check that it will be minus actually here, minus pi, comma f, comma pi. So it means that pi, comma f, comma pi is twice is equal to 0, which is just what we want, right? So this is 0. Okay. So the first part is proved up to this sign issue. And now the second part, which is also quite simple, is even simpler than the first part. It is that you just use the definition. What is the commutator of xf, xg applied to some function h? It is xf of xg of h minus vice versa, xg, xf of h. But by definition, the first line of the definition, this is equal just to the double Poisson brackets, right? F, comma g, comma h minus g, comma f, comma h, which is by Jacobi identity again equal to well, I think the sign is correct, fg, comma h, right? So if you want to check the sign, then we need to change the order here. We get plus, right? So if you want to check the sign, let's check the sign. It is equal to g, h, f. So this sum will be equal to minus h, g, f, right? No, hfg, hfg, like this. And that's precisely this, right? The minus is is obliterated by changing, is removed by changing the order here. So this is true. That means that we have h x of f comma g applied to h, just as I promised. So for every function now we have the Hamilton vector field, and the Hamilton vector fields again constitute as Lie subalgebra with respect to the brackets. However, unlike this symplectic case, where the property 1 actually means that the vector field is in fact locally Hamiltonian. So the property 1 in symplectic case also exists. You also have so by definition of Schouten bracket, this is equal to the Lie derivative of x sub f with pi. And of course, in a symplectic case, we also had this property that when you have a Hamilton vector field and you apply this Lie derivative with respect to this Hamilton vector field to the symplectic form, you get 0, right? And in symplectic case, as you know, locally, if we have the equation L sub x of omega is equal to 0, which is the same, of course, as L sub x of pi equal to 0, because pi is just the inverse of omega, right? Then, in symplectic case, we know that locally x is equal to x sub f for some f. But not so in Poisson case, of course. And let us describe a construction which measures the difference somehow between the properties of being Poisson and being Hamilton. So we will recall again a vector field x Poisson if Lx of pi is equal to 0. So let me describe some construction that allows one to measure, in some sense, the difference between these two properties of being Poisson and being Hamilton. I mean the so-called construction of Lichnerovitsch-Poisson cohomology. Lichnerovitsch-Poisson cohomology. So we consider the following chain of vector spaces C k of M. Let us denote LP here. Let's put LP here for Lichnerovitsch-Poisson to be equal to the space of k vector fields on M. And the differential d pi from Ck LP of M to Ck plus 1 LP of M will be equal to d pi of omega, or probably beta of alpha, will be equal to the. Sometimes I wonder whether it is better to write in one order or another. And pi is the first. Pi alpha. Okay. So let me then write down the claim that d pi square is equal to 0. So to this end, we just compute this. Pi, comma alpha. And since I don't remember the signs, I'll look into my notes. So this is equal to what? It is equal to minus, so it, please check the signs if they're correct. They're equal to alpha pi plus pi, comma alpha. Okay, I think it is like this. And so this term is equal to 0. And this term is equal to minus. So, you know, when we change the order here and here, we get pi, comma alpha. However, the sign that we had will appear from first change in the order here, right? So the sign we get will be minus 1 to the power 2 minus 1, that's 1, times k plus 2 minus 1, right? Huh? Okay, let me recall the graded commutativity of Schouten bracket. It looks like this. We have alpha and beta, so let A be of k degree k, B of degree L, then it is equal to minus 1, k minus 1, L minus 1, beta alpha, right? So this is equal to 2. This is equal to 2, and this is equal to k, say, right? So this element is of degree k plus 1, and this is of degree 2. So when we change the order, we get minus 1 to degree k plus 1 minus 1 times 2 minus 1. And there's just minus to the power k. All right? But then we need to change the order here as well. So this will give us minus 1 to the power k minus 1. And 2 minus 1 is actually not necessary again because it's again 1. So this is equal, this vanishes, right? So this cancels out, this k cancels out, and we just get minus, as I promised. This minus is really important. So what we see is that this is equal to minus dp squared of alpha. So if something is equal to minus itself, then it is 0. At least when the characteristic of the field is not divisible by 2, right? It's not 2. Okay. It's not 2. The characteristic is not 2. Not divisible. It's not 2. Okay, nice. So we now have differential, which scales to 0, squares to 0. And by definition, we say that Lichnerovitsch-Poisson cohomology of M is equal to the cohomology of this complex. Then the discussion concerning Hamilton vector fields and Poisson vector fields can be now written as follows. So what is a Poisson vector field? It is the vector field for which I have this identity. Right? So that means that d pi of x is equal to 0. So x is in C1 LP of M, and x is closed. What does it mean for it to be exact? Actually, it means that x is equal to d pi of some function f. But as I explained, this is of course equal to pi f, and it means that it is precisely up to the sign again. Yeah, okay. But the sign doesn't actually matter, right? When we just change f to minus f, right, we get x sub f, right? So a vector field is now exact with respect to this differential if it is Hamilton. And the difference between being exact and being closed is precisely cohomology, right? You can say that H1 of M is equal to the space of Poisson fields divided by the space of Hamilton fields. In case where when we work with actually symplectic structure, you already know that it's also applicable to symplectic structure. So in symplectic case, every Poisson field is locally Hamilton, and actually you remember that a field is in fact Hamilton field x such that Lx of omega is equal to 0 is Hamilton if and only if, you remember, the form Ix omega, which is closed, you remember, is exact. You remember that d beta is always equal to 0 in that case, but it might not be exact. So we see that, in fact, in that case, H1 LP of M is actually measured by the following space. We take a space of all exact forms, exact one forms, because when we take beta, actually d beta is equal to 0 and raise its indices with respect by omega, we get, of course, some Poisson field. You remember, we discussed this at our previous meeting, right, seminar. Divided by, closed, of course. But here we need exact one forms. So what we have is just H1 the ram of M. The same is true in degree 0, of course, because in degree 0, what do we have in degree 0? What do we have in degree 0? It's even simpler. In degree 0, there are no exact elements in Lichnerovitsch-Poisson cohomology because there are no elements of degree -1. So H0 Lichnerovitsch-Poisson of x of m is just the space of all functions f such that x sub f is equal to 0. Such functions are called Casimir functions. Functions with this property, that is, functions for which Hamilton vector fields vanish identically, are called Casimirs, or Poisson central functions. By the way, not quite sure, well, who was this Casimir. I believe that he was some Italian guy, actually, in spite of the fact that his family name sounds like Polish. I think he was Italian, as far as I can remember, but I'm not sure. I need to check. Casimir function or Poisson central function. Poisson central comes from the following easy observation. F is Casimir if and only if the Poisson bracket of f with g is equal to 0 for all g. Because this is just equal to xf of g by definition, right? So that's when something commutes with everything, it's called central. Okay, so H0 of LP on M is just the space of all Casimir functions on M. And in case when M is in fact symplectic, then the condition of being Casimir means that df is equal to 0. So if M is symplectic, in fact, then x of sub f is equal to 0 identically if and only if df is equal to 0, because this is equal just to raising of the indices with respect to non-degenerate bivector of df. So what does it mean that df is identically 0? It means that f is just constant. So we see that in that case, H0 of LP in symplectic case of M is equal to just the space of constant functions, which is again the same as H0 in the RAM of M. And in fact, I'm going to prove right now that it is always the case. That if M is symplectic, then of course this Hamilton Lichnerovitsch-Poisson cohomology is always equal to the RAM cohomology. That's just an easy observation now. So we take, let me prove the following claim. Claim if if M is symplectic, then Lichnerovitsch-Poisson cohomology of M is always equal to the RAM cohomology of M. And the proof is pretty simple. Consider the map given by raising the indices completely, a complete raising of the indices. I denoted by the same symbol pi sharp, and this map is from differential forms on M to polyvector fields, of course, on M, right? This is complete raising of the indices, the raising of all the indices with respect to pi. This is invertible, of course. It is just the operation of lowering the indices. I think it is like this. This is the sharp, right? And this is the flat, or vice versa. I'm not sure about this. I'm not good in music. So this operation goes from polyvector fields on M to differential forms on M. And they are inverse. Now it only remains to show that these two operations do in fact intertwine the differentials, the RAM differential with the Poisson, Lichnerovitsch-Poisson differential.
This by sharp is a contraction.
Yeah. So this is a contraction. It's actually in coordinate sense. You just take all the indices and contract them with coefficients of the symplectic form. So what's the question?
I thought that in music theory it should be bemol.
But that's not in English. You know, there is.
Yeah,
In English, they use different terms in music theory. So that's something
I
that.
thought also it should be a different symbol,
Huh?
like B.
Oh, maybe. I'm not sure. I am bad in music. I'm sorry. Never attended a class on music.
Yeah, I thought it should be B.
Maybe. Okay, whatever. Take whatever symbol you want and use it. I'll stick to this just for the sake of, of constancy. I used this already, so I probably stick to it. In any case, let us show that, for instance, it's sufficient to show that if you take this operator and apply it to d pi of some alpha, it will be equal to the same as the RAM differential applied to this operator applied to alpha. So if this is true, and of course the opposite is also true because these two operators are mutually inverse, right? Omega and pi are mutually inverse. So let me check this. And I'm not going to do this in coordinates, although it is possible, but let us do this by some abstract reasoning. So we just consider the operator which you obtain in this way. The operator how do you call this? Omega composed with d pi composed with pi sharp. It is the operator from differential forms to differential forms which raises degrees by 1, right? And has plenty of properties. So what are the properties? First of all, this operator, let's denote it by d tilde. D tilde square is equal to 0, and that's true because d pi square is equal to 0, right? D pi square is to 0. Then what else do we have? D tilde actually verifies Leibniz rule. Graded Leibniz rule. Leibniz rule. And that's again very simple because both pi sharp and omega flat, let's put it this way, verify actually homomorphism with respect to the wedge product. The wedge product. And actually, d pi also verifies graded Leibniz rule just because the Schouten bracket verifies this graded Leibniz rule. Verifies graded Leibniz rule. because the Schouten bracket does. Right? So it only remains now. So since you know that the operator on differential forms is uniquely defined by these two properties and by its values on low degrees elements, right? So let's check that these two operators, d tilde and usual d, agree on functions and on, say, differential one forms, and that's enough. I think even functions are enough. So let's check that on functions. So if f is a function then d tilde of f, what is it equal to? It is equal to omega sharp of d pi of what? Yeah, of pi sharp of f, right? Like this. Now pi sharp of f is just f, so we need to consider d pi of f, right? And d pi of f is the Hamilton field associated with f, right? So that's just omega of x sub f. On the other hand, it is equal to the pi sharp of df. But since omega and pi sharp are inverse, mutually inverse, so we just get df. And that actually completes the proof, because since this holds, these two operators, d and d tilde, have the same properties, 1 and 2, and also agree on the elements of degree 0, they should agree everywhere. And that's all. Okay. However, in case of genuine Poisson manifold, genuine Poisson structure, Lichnerovitsch-Poisson cohomology is quite complicated stuff. In your homework, you can see one problem which is marked with a star, with asterisk, where you are asked to compute Lichnerovitsch-Poisson cohomology on R2 for some very simple Poisson structure on degree on the plane. And turns out it is possible, it can be done, but the computation is quite complicated. Actually, I think I gave a reference to some article by some Japanese guy, 30 pages long about that, maybe a bit less, where he accurately computes this cohomology. It's not a one page thing to compute it, definitely. He actually computes more than that, so there are more than just, you cannot say that he computes this on 30 pages, but it definitely takes him more than 1 page to compute that example. Okay, so let me, so how much time do I still have? So now let me formulate the deformation-quantisation problem for Poisson manifold. It is an easy thing, but I think it is worth to have it stated, explicitly at a certain moment. Let m comma pi be a Poisson manifold then to construct a deformation quantization of m comma pi means to find an associative H bar linear star product on the space C infinity of M, enhanced by the taking formal power series with respect to the variable H bar.
Simply Moyle form.
Not Moyle. Well, the Moyle was an example of this. Now this is much more general, much more general. Even if you take M equal to some Euclidean space, to a fine space, even in that case, when you take a genuine Poisson structure on M, constructing this product is actually quite a big problem. And in fact, if you can do this for arbitrary Poisson structure on a Euclidean space, on an affine space, then you would be able to do this everywhere. I'll speak about this later. Okay, here, such that first, for all f g in C infinity of M, f star g would be equal to I think, okay, let me put it like this, f times g plus sum h bar to the power k bk of f comma g, where bk f comma g by differential operators. Actually can remove f and g here, are some bidifferential operators. Okay. 2 P1 of f comma g is such. Okay, I probably better put it like this, not B1. Let's put it like this: f star g minus g star f. I'm not caring about B1, in fact, I'm caring about this, divided by h bar, will be equal to the Poisson bracket of f and g with respect to pi, plus something which is, okay, which has the form h bar times something, right? So modulo h bar, it is like this. In fact, we can replace the condition number 2. I'll explain how and in what manner can be replaced by the condition I was going to write down at first. By the condition that B1 of fg is equal to 1/2 of f comma g. It's not just the same, but it is equivalent, in fact. So there are usually 2 more conditions which are sometimes added. But in the text which I looked into, nobody actually cared about these 2 conditions. Except for the first one is sometimes just evident, but even then it is not usually cared about. So condition number 3 is that f star 1 is equal to f and is equal to 1 star f. So in fact, it just means that the unit function is just equal to the unit with respect to the star product. Remains unit with respect to the star product. And the condition number 4 this technical condition which appeared a few times, which already emerged a few times in our conversations, that's a condition of symmetricity of bk. So bk of fg is equal to -1 to the power k bk of gf. So these two conditions rarely make their way to modern texts, but sometimes they are important. Nice. So let me continue with these definitions, the statement of the problem which we are going to deal with further. Just like in case of Moyle product, we will distinguish equivalent and not equivalent star products. So not equivalent means that they're not equivalent, that's all. So sorry for the tautology, but equivalent means that the following is true. So let star 1, star 2 be two star products on C infinity M enhanced by H bar. Then we'll say that star 1 is equivalent to star 2 if there exists a formal power series of differential operators. So beginning with the identical operator, but then we'll have H bar times T1 plus H bar squared times T2 and so on. Ti are differential operators on M in the usual sense, not polydifferential, but just usual differential operators, such that T of F star 1G is equal to T of F star 2 T of G. Of course, since T is invertible, we can just put it to one side, and that will mean that this is in fact equivalence relation, not just something. So final, ultimate problem, ultimate deformation-quantization problem would be not just to construct a star product, but also to classify it. So finally, the deformation-quantization problem, on M pi would be, or is, to first construct a star product, and number two, to classify such products up to isomorphism, up to equivalence. Well, sometimes you can a little bit relax this one by something not that simple. I mean, of course, if you have a Poisson manifold and you have some, say, Poissonomorphism, the morphism of Poisson manifolds which preserves the Poisson structure, right? Diffeomorphism which preserves the Poisson structure, then you can use this diffeomorphism to change a little bit the star product. You just compose it with the star product you have. And it would mean that we just allow diffeomorphisms here, not just identity operator, but diffeomorphisms. But that's just a simple generalization. So in the future, I'm going to deal with this problem, and I'm going to describe different examples and different constructions which allow people to solve this problem in various situations. If time permits, let me begin with an example, a classical example of genuine deformation-quantization of a genuine Poisson manifold. It will be quite a simple example, but still it will not be symplectic. It will not be, so it will be genuine Poisson case. Example. So first of all, we take M equal to the dual space of a Lie algebra. In that case, I will restrict my attention for a while to just a situation where functions f and g are not genuine smooth functions, but are rather polynomial functions on g check. They are elements of the symmetric powers of G itself. We need to define f star G. So there are a few ways you can do this, and I'll discuss these ways in future, when we talk about some other constructions. But now I'll just use the famous Poincaré-Berhouf-Witt theorem. I wonder whether you have heard about this theorem or not. Yes. I just wonder whether you have talked about universal envelopment algebra before. Yes. Okay, nice. So, nice. So let us take the universal envelopment algebra UG of G. Let me recall that it is just a tensor algebra of G, where you quotient out the relation x tensor y minus y tensor x is equal to the commutator x and y in the algebra sense. Then by Poincaré-Berhouf-Witt theorem, so there are different ways you can formulate and prove this Poincaré-Berhouf-Witt theorem. I will need the following very explicit, well, rather explicit, not very explicit, rather explicit construction. Consider the map. Consider the map sigma from SG to the universal envelopment algebra of G, given by the following formula. You take so you can define it universally by just saying that sigma of x to the power p is equal to x to the power p on the right. And that actually gives you a unique way to extend it from linear part to all polynomials, but probably better to write down an explicit formula. You just take the monomial x1, xp, so xi are just some elements in G. So every element in this symmetric power of G has is a linear combination of such elements. Then you just put the right-hand side is equal to 1 over p factorial, and sum over all permutations S in SP of x S1 dot x SP. So on the right-hand side, dots mean the product in the universal envelopment algebra, whereas on the left-hand side, dots mean the product in the symmetric algebra. So on the left, the product is commutative, and the
Shouldn't it be from UG to SG? We symmetrize it.
Yes, that's from SG to UG precisely, as I said.
Not
You cannot do it on the opposite. And that's the problem. There is no explicit formula, explicit map from UG to SG. You cannot write it down in this way. Using the claim of Poincare-Berhoff theorem, it is easy to show that sigma is a linear isomorphism. Not just linear, but actually is an isomorphism of G module, where you allow the group G act on both sides by conjugations. So that's actually a homomorphism of G modules. Moreover, it's even an isomorphism of coalgebras. An isomorphism of coalgebras. But I don't know if you have heard what were coalgebras. Have you heard about coalgebras or not? We will not use it here, so I just put it in some kind of parenthesis. You can say it like this, but you can give a more explicit formula, but that's not matter. It's even an isomorphism of coalgebras, but of course not an isomorphism of algebras. Right? In theory, you can find inverse map in theory from right to left. And we will make use of this theoretical map to define the star product on SG. So first I'll define some deformed product in SG. Put F star G in SG to be given by the formula, take the inverse of sigma of F times sigma of G. It gives you some associative product in SG. The associativity is evident because the product in universal development algebra is associative, right? When you do this composition, sigma and sigma minus first cancel out, you just get the triple product of sigma F, sigma G, and sigma H, which is of course the same in both orders, right? You can actually easily introduce H bar into the play if you want to, right? If you want to introduce H bar, you just do the following trick. You modify to introduce H bar. You modify the definition of universal development algebra by placing H bar into the definition of this algebra here. Right. So now this sigma actually gives you a map, an H-bar linear map from SG H-bar to UH bar G. Maybe you need to, probably you need to use H bar here already, right? If you really want to do something like that, you take the tensor product over H bar, of course. So it's something like that. But that's just a technical thing. It's not very hard. What is interesting is to check that this product in this case verifies the conditions we have. So the hardest part of it is to prove that the coefficients bk of this product are actually given by certain bidifferential operators, right? It is the hardest part. It is easy to see that the star product of this form always begins with f times g in the usual sense, plus some elements of lower degrees. This actually follows from your from the proof of Poincare-Berhoff-Witt theorem. It's always like this. The top degree element is always just f times g, nothing else. But as far as the lower degree components are concerned, it is not, you can actually, you need to work hard to prove that they are in fact bidifferential operators. I'll do this next time. Let's now just describe the term B1. Let's do this first for f and g of very simple form. F and g in linear functions. Which is, of course, a subspace in SG, right? In that case, what do we have? F star g will be equal to sigma minus first of, well, of course, sigma of x is just x, and we just get x times y. So how, and then here's the problem, how do we define the inverse map, right? So let me give some construction which probably explains this. Take sigma of x dot y. It will be equal to 1/2 of x. Probably better to omit dot here and use dot just to designate the product in universal enveloping algebra, right? So here we'll have x dot y minus y dot x. So this is equal to what? It is equal to 1/2 of the bracket x and y. Oh, sorry, plus. Of course, plus, not minus. Almost. So almost. So it's equal to almost this. So 1/2. I still have this x dot y minus y dot x, right? Plus twice y dot x. Yeah. So what do we have? So sigma of x, y is equal to y x y dot x. I hope it's not, so is it minus and plus, right? I think it's correct, okay. Plus 1/2 x comma y. Nice. So what? But this is just equal to sigma. Continue. It is equal to y dot x plus 1/2 sigma of x comma y. Because on linear elements, sigma is just identity map, nothing else. Right? Yeah, and I forgot about h bar. So h bar is necessary here because in UH you have h bar appearing in front of commutator every time you commute, right? So you have this. Okay, nice. So what do we have here? It is equal to what? it is equal to sigma minus first is preserved. So here we'll have x times y, right? Sigma of xy. You see? You see what I did? I used this equation to say that y dot x is equal to sigma xy minus 1/2 times h bar sigma commutator xy. Right? So I just change the order. Here we just have this. Change the order of y and x, and I have that sigma of xy is equal, sorry, y dot x dot y, just what we have here, is equal to sigma of xy plus, right? Plus h bar divided by 2 sigma of commutator x and y. The sign is correct. But now sigma and sigma minus first, they cancel out. And just as I promised, what I have is equal to x times y plus h bar divided by 2 x comma y. So you see this formula, and this is precisely a bracket of f and g by definition. So this formula holds on linear functions. And now we need to work by universal properties to show that the same will hold for arbitrary functions. How much time do I have? Is it worth to start this discussion or not?